Hello folks, this tutorial belongs to the playlist which is called Transition to 3D Experience from the Abacus CAE program in my YouTube channel. It deals with the coupling constraints that is available in Abacus and of course the Abacus program being the solver in 3D Experience is also available there. So the way I conduct these tutorials is that I basically find stuff that is done on YouTube in a step-by-step fashion using the Abacus CAE, and I replicate the steps in order to show the viewer what are the differences, how the interface changes, and that change is substantial uh, from the CAE program to the 3D Experiences platform. Now, this particular tutorial dealing with coupling constraints is taken from the channel of Dr. Petit, who's at the University of Alberta, and he does this problem using the Abacus CAE in a very organized and uh, methodical manner. So I'm going to replicate the steps. The problem is shown there. It's made of basically two parts which are welded, perfectly welded together. The left side, the left face is clamped, and this column is given, the top of it is given a horizontal displacement of 100 millimeter to the right and a rotation of 90 degrees in this direction. The dimensions are given here, and I should point out that because this is perfectly welded, in fact, one can solve this problem as a single part. However, we're not going to do that. We're going to do it as an assembly. Now, the coupling that we're talking about is the, the motion of that top face. You'll see that I will create a coupling with a reference node up there, and we just move it to the right. The other thing is that this material is assumed to be made of steel, but the thing goes in the plastic range, obviously, because these are large displacement compared to the sizes that you can see down here. And uh, the true stress versus true strain or plastic strain, true stress versus plastic strain is given here. And uh, we're going to do this problem in two steps. Although, I forgot to mention that that displacement that I apply on the top, the displacement and the rotation that I apply on the top, uh, after the column deflects, it is removed. Okay, so it's a two-step process. One is to apply the load or displacement up there and the rotation, and then in the second step you remove that load. Both of them, this is a static problem, and both of them are, I'm assuming there's a dummy duration of 1 second for each. I will be doing a sweep hex element using the sweep option, and there are some other slides here, and I'm going to go through them very quickly. But after we do, while we're doing the problem, I'll come back to these slides uh, as needed. Okay, so what we need to do is to define a coupling connection. So this is the action bar at the bottom of the screen for 3D experience, and there's something called coupling. So under the connections tab, there's something called coupling. So what we're going to do is we're going to create a point up there. So we call it reference node, and then couple that with the top of this column. Okay, so what that means is that the motion of this top of this is exactly the same as the motion of the top. That's what is called reference point. Okay, we'll come to these in a few minutes. And as far as the connection between that column and the plate, bottom plate is concerned, I'm going to use the contact detection, although there are other ways of doing it, contact detection, and because they're uh, perfectly welded, when 3D Experience identifies where they are, then we're going to say tie them together, okay, as if they were welded. So we do get something like that, you'll see. Now, So what happens is that there is very little stress in that plate. However, this column uh, shows significant plastic deformation. So if you look at the equivalent plastic strain in this part, it's 4%, 4.8, almost 5%, and that's substantial. Now, I want to point out to you that if we did this problem by pushing the top to the right, as we are doing it here, and giving the rotation, and then pushing it back to where it was and remove that rotation, the the the, the, the result is not going to be the same. Okay. For example, what happens here, if you remove the load, this column will spring back, but it will never go to that position. Okay. However, if you want to create some kind of cyclic loading, you push this thing to the right, and then you basically push it to the left, okay, to that location, and there is some accumulated plastic strain, which is 10%. You can see that. Uh, I will do the first problem, and then after I finish it, I come and repeat that with this second scenario, and in fact, we're going to create that. All right. I want to point out to you that this problem, the one down here, can also be done in a single step, but the only thing is that you have to define an amplitude for that single step, which looks like that. Okay, single uh, amplitude for that displacement variation, which is going to be like that. Now, I'm not going to do it with the amplitude, so I'll do it again in two steps because, uh, yeah. Now, at some point, you're going to see this screen because after we create the first step, in the second step that we create, we have to remove these two loads, and this is how we're going to do that, okay? Because generally speaking, if you go from step to step, information is propagated, but we don't want this displacement and rotation to be propagated to step two. So we basically, after it's, because it's done automatically, we're going to remove them, okay? So let's go ahead and do it. As I said, I'll come back to these slides as needed. Let's go to the interface. Here is the 3D Experience interface. We already have an assembly here, so let me go ahead and insert my first 3D part, which is going to be the plate that I'm going to make. I will not do the renaming and things like that. Essentially, this is the plate. So the first one is the plate, okay? Uh, the bottom plate, horizontal plate. So let's go make it. Okay, so on that horizontal plane, I will sketch a 200 millimeter by 200 millimeter rectangle. That's going to be the bottom plate. Dimension it. So this is 200, and this is 200, and we're going to exit and pad this thing by 10 millimeter. There's the icon for the pad, 10 millimeter, and this is what we're going to get. Okay. Well, why don't we apply our material property on this, because the whole thing is made out of the same material, but this column and this plate. So let's go ahead and go to tools and create a material. I'll call this thing steel October 19, 2023. Okay, and we say okay. That's going to be created, but there's no numbers in it yet. So we're going to apply it, and then we're going to here October 19, 2023. Oh, I called it steel, right? It's not this one. So let me go ahead and find out. Uh, Let me try one more time. Let's browse it. Material browser, because it takes some time for that thing to be reflected in the database. Right here, steel October 19, 2023. So I say apply and close that. So we're going to apply it to this part basically, and green check mark, and now we're going to input our material. So double click on this, All right, so it's structures, general option. We don't need the density, so we don't need that. Abacus multiphysics, mechanical, elasticity, elastic, and 200,000 megapascal or 200 GPa, but put down 200,000 megapascal and Poisson ratio 0.3. And then we go to plasticity, metal plasticity, plastic. So where we have 400 plastic strain of 0, so that's the yield strength, and then 600, and the plastic strain is 0.3. I'm pretty sure that's what it was. Check it out. 600, yep, 0.3. Very good. So we say, okay, all right. Now we're going to insert our column, okay, because remember, we're doing it as an assembly. So we go all the way to the top, right-click, insert, a second 3D part, which is going to be my column. Ordinarily, I rename these things to have the right designation, but I just left it like that. So double click on this, let's make it. So on that top plate, I will sketch. Why don't I draw a sketch rectangle here? We're going to put dimensions on it in a minute. So this is 10, and this is 10 millimeters. And let me bring this thing and put it there. Okay. So distance between this, dimension between this, control that point. No, try again. This point, control that point. I'm going to put dimension, but right click and say coincidence, so that it basically puts it in that location. Exit and pad this thing by 200 millimeters. Okay, so pad it under essentials. Here's a pad, the direction I flip, and 200 millimeters. Good. So this is going to be the column. And it's going to have the same material. So while we're at it, so let's go ahead to tools, browse material browser, and it was steel. Okay, steel October 19, apply. Already the numbers, the data is put in there, so I'm going to done with that. I'll put it in the second piece, green check mark, and it's there, as you can see, right there. Then what do we? Let's create a reference point up here. And while we're in this part, so we go under essential, a point. You can either type the coordinates, or another way of doing it, say on a curve, on this curve, some distance of 210, for example, millimeter. There we are. It's right there. Okay. Maybe I should make this thing a little bit higher so that I can see it. Maybe 220. Yeah, that's better. Okay, good. Now we're going to save this thing. So we go save here. All right, let me go all the way to the top, and go to 3D corners, the button here, and go to the meshing module. The meshing module is really this structural model creation. You click on it, empty FEA. This window opens up, and make sure you get it if you're replicating these steps, because this tells you that I have two parts in this finite model that I'm creating. Which one of these should participate? Obviously, both of them. Both of the parts are going to be involved there. So I just checked the whole thing. Both of these are going to be selected. All right, good. Now, we have to do the meshing ourselves. Let's do the meshing for this plate first. Under the meshing tab, there's a meshing tab. We go to sweep, go here, expand it so that you get sweep 3D mesh, And what you see there is actually this slide, okay? Sweep, and then you're going to select it. The size of it is 3.3 because I want 3 elements through this thickness, and this was 10 millimeter, so 3.3 will do the job. And this is 3 layers, okay, and it's linear, okay, and we say mesh it. Oops, I forgot to select the support. There's the support, mesh it. There we are. So this is the mesh for the plate. Say okay. Why don't we do the mesh for this column 2? So we do the same thing. Sweep 3D, select that. Now, because of the way these colors are selected, it means that it's going to sweep in this direction. Okay, the layers is going to be in this direction. So I want 3, and the size is the same. So we mesh it. Okay. If it had done like that, magenta and purple were on these two ends, then you would be sort of 60 layers, something like that. But the size is going to be the same. Now, we have to create our properties. So you select the properties, in other words, the material and things like that, you have to specify. Here's a solid section. You click on it. Why don't we go ahead and first do this bottom one? Now notice that if I select this, the part is going to be picked, part body. If not, you can go to the tree actually. It's easier for you. You can select from here. Notice that the proper material is taken. And now we do this guy. See, again, part body is selected for the column and material is correct. Say all right. So both the mesh and the properties are selected here. All right, now I want to do that coupling thing over here. First of all, maybe I should hide my mesh. So I go right click visibility manager. There are different ways of doing it, but you can hide the mesh. There's the part. Good. So you click on the connections. This guy pops up, and now we're going to this slide. Connections. This guy pops up, and coupling is right there. So we go here. We select the coupling. Okay. On the side. So one support is this top face. The other support is that point. So see, coupling to a point. And we want a kinematic coupling, and all of these are checked. So the degrees of freedom of all the points on this plate are the same. Top plate are the same as the degrees of freedom of that reference point. We coupled all of them. So this slide is actually that, as you can see. Okay. All right. So let's go ahead. And notice that if you look closely, there are 4 lines here, which is hard to see because of the background. But if the background was blue or something, then you can see these white lines here. We say, okay. So a coupling has been created right there. All right. And that's pretty much it as far as this end is concerned. Okay. Let's do a quick save here. Okay. So now we're going to go to scenario. This is the one that we have a implicit. This is implicit dynamics here. We are doing a static problem, but this will do the job for us. If you have some other requirements such as explicit dynamics and things like that, you don't find the license here. Your license is over there. But structural scenario creation is what we want. You click on it. Okay. And here it says the type, the analysis type is structural, and the finite element model not selected. So we're going to select it. That's the one that we just made. This is the one that we just made. Say OK. Good. Okay. The reason that there is an exclamation mark here, red, it says no procedures exist. So Here we go to the procedures tab right there, and static step. This is step 1. And for the time dummy, this is a dummy time. I put down here point, initial time 0.1, maximum time. I'll put down here point 1, maximum time increment also point 1. Okay, point 1, and to be in line with what that reference is doing, I think this was changed to the minimum time increment was changed 10 to the minus 10. We never need that smaller time increment, but I did it anyway. And notice that here the geometric nonlinearity is activated because we are doing, this is by default activated, and we want to solve a nonlinear problem. Obviously, it's plasticity. So we say okay. Good. The other thing is that the type of the element, if you look at it here, notice, by the way, these are both green now. If you expand this thing and expand the plus sign here, global element type assignment. So this is uh, 8-noded linear element, but it's not reduced integration. So I can change that to R. And what you see here is now this this slide right there. It's this dialog box. Okay. All right. Let me say okay. All right. As far as the boundary condition is concerned, that back side of this is clamped. I can do clamp, or I can do, for example, fixed displacement, because rotations don't count for a solid element. So either clamp or this will do. Okay. And then up here, I want to apply my displacement on this reference point, because whatever you do here is going to get transmitted to that through the coupling to that top face. So how do we do this? We go to translation. This is velocity. Here's translation. Apply translation. The support is this point, this reference point. The direction is direction Y. The value, it's very easy to make a mistake here. This is 100 millimeter, not 100 meters, okay? So 100, I should have changed my my units, but which is going to be point 0.1 meter, okay? That's good. And then we apply a rotation. So right here, this was translation. Here is the rotation, same point. Okay. In about the X, this is the way we want to do it, but not like that, minus 90. Let's check, see if it's right. Yeah, because this is how it's drawn here, like that. Okay. All right, so that takes care of this. Now, we have to create the tight connection between these two. Okay, so there are different ways of doing it, but what I'm going to do is the following. I'm going to go to interactions. Please note that there are other ways of doing it too. So here it says contact detection. In other words, tell me what faces are in contact with each other within the tolerance that's specified. So this dialog box open up. And what I'm showing you here now is actually this. Okay, so first of all, we have to make sure that the tie surface is checked and find the surfaces, okay, is clicked. So I want to make sure that the surfaces are tied together. And this is very important, find surface pair, because right now it hasn't done it. Notice that I cannot even close these things. But as soon as I say find surface pairs, apply, it finds it for me. There is one surface which is at the bottom of that. Is that the pink or magenta? And there is a green one on this side. So it found it for me without me doing any work. Within that tolerance, obviously, that's fine. And if you look at it now, actually, it created a surface to surface contact. So you go, not contact, interaction, tied right here. If you look at this surface-based contact, they're tied together. Okay, if I double click on this, either from here or from there, it says they are tied together, tied surfaces. I didn't do that, but that tie that I checked in the other box led into this. Okay, I am pretty sure this is it. Save it. Let's do a quick model check. So under simulation, quick model check, anything obvious that we forgot may pop up here. No issue there. There's a check mark, green check mark. This is a scenario check. Again, certain things that you need for scenario, loads, or boundary conditions, and things like that, that may have been wrong, whatever are going to pop up here. I'm pretty sure that this is fine. Now this is not running yet, it's just checking right there. So we're going to say okay. Now it's going to do the checking, simulation checks. There may be some warning messages. It's a good idea people to read it. I mean, obviously, if it's error, it's not going to run, but there are some warning messages. Let's see what this thing says. Okay, output request has been removed. All right, fine. Okay, this is done. Notice that it is done. No problem. Now, to run it, you say simulate, wait for the dialog box to open up. This is only step one. Okay, we have a choice of running this thing and adding step two to it. That's one option, but that's not what I want to do. I forgot to do the other one. As simple as that. So I'm not going to run it. I will, as soon as it says I'm ready to run, say cancel. Okay, so cancel, don't do it, because I want to insert my second step. I really didn't have to do this because I ended up coming and doing something that I should have done earlier. So we go to the second step procedure, another static step, and we use the same information, point one, okay? Now, notice that everything that we did up there is propagated. In other words, we had apply translation and rotation is here in the second step, etc. Now, that clamp stuff is all the way on the top. That's at the initial stage. It carries over. Now, I don't want these things, and there are different ways of doing it. I can go right-click here, remove applied rotation, right-click, remove applied translation. But I want to show you something else that's very useful. You click on the feature manager, this guy, and what I'm going to show you now is this last item. So I'm going to click on that. Remember, you can remove these, no problem. But I want to show you a different way. So you click on this. Oh, okay, sorry, this one, feature manager, and say show me the applied rotation and show me the applied translation. Notice that these two, which are in step one, are also propagated to step two. I don't want this thing, so I can do the removing from here. Right click, remove applied rotation, right click, remove applied translation, which I could have done by doing it going through the tree. And this is fine. Now, you can also do the checking and running through here, but I'm not going to do that. I closed it, so I go to simulation. Okay, notice that these things are gone. There are no applied translation or rotation in the second step. Uh, Believe me, these are fine, but I always try to go through it at least once. These are things that I did earlier, and I said I forgot to put my second step in the case. That's why I didn't run it. I just went back and did the second step and etc. And this is the simulation check, which is fine. It's going to do it for us. And the running is going to come at the end. It's that last one which says simulate. Okay, good. Close, and now simulate. This means run. Now, when the dialog box opens up here, I'm going to say OK, and we let it start the iterations, but I'm going to pause the video because this run is going to take, this particular analysis is going to take about 10-15 minutes. So I'm not going to let it run and just for you to watch the screen, but I'm going to pause the video. Once it's done, then I'm going to come back and start it and do the post-processing together with you. All right, so I'm going to say OK. In other words, start running. And iterations, it will struggle in the first couple of increments, but it goes very smoothly, but it takes about 10-15 minutes. So I'm going to pause it at that point, and then once it finishes, I'll come back. See, it's struggling here. Did not converge, but now it's going to go. Okay, good. So 10%. Okay, so I'm going to pause the video. Okay, I am back. This thing finished, so let me close that. And here is what you've got. All right, move this thing on the side. Okay, this is the initial position. No displacement has been applied, but gradually we start applying the displacement. You can see that, okay? This is the von Mises stress, and you can see that as you go further down, at 1 second, of course, this is pseudo time. 1 second, this reaches 100 millimeter to the right, and it rotates by 90 degrees. There. So this is step one. So step two, the load is removed. So we go here to step two, and of course, step two, this is the end of step one, beginning of step two. The load is being removed, and notice that this thing springs back. Okay? Oops. This thing springs back. And there. So it stops here. Okay, so I just want to check something, and that is I made a mistake here. See that? This was supposed to be 200, it's supposed to be 100 millimeter. Inadvertently, I specified 200. Okay, this is why when you go to the displacement, I'm not sure actually. So I'm sorry, just a second. Displacement, although this is 100, it is 100 millimeter. I'm sorry. So this is the displacement at the beginning of step two, which is 100 millimeter. Now, we gradually remove that 100 millimeter displacement eventually because of it springs back, but it doesn't go all the way to the end because it's plasticity. So let me do a couple of things for you here. First of all, we can animate this thing. This thing is displacement. This thing smaller. This is displacement, and you can animate it. It goes to 100 millimeter. See that? And then this is step two. Okay, so let's animate it again. Step two, remove the load, goes back, and then of course stops there. You can also look at the plastic strain. Okay, Let me get out of this animation mode. This is step one, plastic strain. So you go all the way to the end. It has this much plastic strain, okay, roughly 5%. And what I'm showing you is now this slide, this one, okay? It's exactly the same number. So when you go to step two, okay, notice that these things, you go to step two, uh, this is the end of step one. This thing springs back, but the value of the plastic strain does not change. Yes, it does spring back, but the strain, plastic strain, is built into it, and it doesn't change. Okay. All right. So is that clear? You see, this was the plastic strain after we moved it for 100 millimeter and rotated it. When you remove the load, yes, it springs back, but the locked in plastic strain stays. So what I want to do now is go and do the following. Let me go back to the scenario. Okay. All right. Good. So in static step two, now we want to apply a load which pushes this thing back to zero and rotation back to zero. So we are in step two. We go back to boundary condition, apply rotation to that same point. Let me hide these things. I don't want to see it. Actually, let me hide my step. Cancel that for a second. Let's look at just step two, and I don't want to see these are these, so I'm going to hide. Okay, hide, hide. Okay, so we go to boundary condition, apply rotation at that point, and in the direction X, and you want to push it back to zero. Now, zero doesn't have a direction. That's why it stays the same. It doesn't go the other way around. So that's fine. And translation, notice that here we have a rotation right there. You see that? Okay. And translation, that same point. You want to send it back to zero in the direction Y. And once again, notice that zero does not have a, to the right or to the left, basically. So 0 millimeter, which is incidentally the same as 0 meters. That's fine. Good. So now we're going to run this thing again, and I'm not going to bother, actually, I'm not going to bother doing the model check and scenario check because I'm pretty sure it's going to work. What we did, the only difference that we did is that we also have specified these things in step two. Before we removed it, remember? Now we're going to specify it so that it goes back to where it started from. And I'm going to, when I run it, I'm going to stop the video because it's going to take another uh, uh, 10-15 minutes, and then we come back and look at the stuff. Okay, so simulate. Just give it a minute. I'm waiting for this dialog box to open up so that I can say okay and let it run. It's still getting organized, basically. Right there. And I say okay, so it's going to do pushing to the right by 100 millimeter, pushing back to where it was, to basically zero location. You say okay, and okay. Iterations. I'm going to stop the video in a few seconds. Once this thing starts iterating, going through different increments. Okay. The first 1 minute obviously is exactly what we had before. So I'm going to stop the video. Okay, I'm back. This thing took another 25 minutes to run. So here's the situation. In the first run that I made and showed you the results, I pushed that top to the right by 100 millimeter and rotated it 90 degrees, and then removed that, removed the load and the rotation. Okay. So what happens is that that column springs back to a position which is not the initial position because of plasticity. In this run, I'm pushing it to the right and rotating about 90 degrees exactly. So the first half of this is exactly what we did before. But then when it reaches that end, I then push it back. I won't remove the load. I just push it back to take it to where it started and take that rotation away. And that is a different problem. Okay. So that's what we're doing now. We look at the results. We close this. So this is let me put this is the let me take you to step one, where we start pushing it. The first this is going to be exactly what we had before. If you go all the way to the end of step one, this is exactly what we had before. Look at the numbers, the same. Now when we go to step two, okay, let's go back to the beginning of step two, which is where we left off in step one, right there. Now we're pushing this thing to the left. Removing the load means that we are pushing it to the left with some force. Okay, notice that it keeps going and the plastic strain is building up. It doesn't stay the same. See that? And at the very end, it reaches that position. Okay, so when I push this thing back to where it started, there's this much plastic strain, about 10% plastic strain that is built up in it. And what I'm showing you is this. Okay. Now, as I said, this could have been done in one step. The only thing is that in a single step, not in two steps, we could have done it, except that you have to apply an amplitude of basically taking it to 100 millimeters and then from 100 millimeter to down to 0. Okay. In a total of 1 second. All right. So let's also do an animation here. This is when it goes to the right with that 100 millimeter displacement and rotation. And this is when we are pushing it back. We're not letting it go, remove the load, we're pushing it back. Okay, that's it. I hope you found this thing useful.